Hi, Mr. Myers here. In the last class meeting, we talked about single and double replacement reactions as part of our 5 reaction types. And I wanted to go over some of the particulars about them as I alluded to some specific tools we can use with these reactions. So to review, single replacement is a reaction in which an element takes the place of a second element that is already in the compound. So we have an element, for example, A, and it is going to replace B in the next compound. And so what we get is a new compound and a new element. As this says here, what we see on both sides of the equation is one element and one compound, but note that the element and the compound in question are different on either side of the reaction. Now, this only occurs if the end products are more stable than the reactants. Okay, so more stable, this has to deal with reactivity of the metals. To look at this, we use something called the activity series, which is shown on the right. And this is a useful guide for predicting the products of single replacement reactions. Essentially, if we compared any two metals on the metal side, the higher the metal on the chart, the more reactive the element is. So higher equals more reactive, and then the reaction will proceed. So let's look at an example here of aluminum reacting with hydrochloric acid. We want to know, is aluminum going to replace hydrogen in this reaction? Okay, we know it's going to replace hydrogen because chlorine as a metal is a nonmetal, and aluminum here is a metal. So is aluminum going to go and be with chlorine and essentially swap out or kick out the H? Well, we need to identify where each of them are on the list. So we find aluminum right here compared to hydrogen, which is down below. The fact that aluminum is higher right here, it's higher up on the list than hydrogen, means it's a more active metal or more reactive. And so this reaction does work, and aluminum will replace the H. So an ionic compound is formed here. We get aluminum, which you should know has a +3 charge, reacts or combines with chloride, which is a -1. If you do the crisscross, you get a formula of AlCl3. And then hydrogen is not just a hydrogen atom by itself, but instead we recall that it's diatomic, and so it's H2 as a gas. Okay, so this reaction does work because aluminum is able to replace the H here. Let's look at another example where there is no reaction. Okay, so this is an example where there is no reaction. Okay, so in this example, we take silver and see if it reacts with copper-2 nitrate. Okay, so we're looking at silver here versus copper. Both of them are metals, so we're going to use the activity of the metals, and we identify where each is. Silver is down near the bottom, but copper is above it. So the fact that silver is below copper means that there is no reaction here. Okay, the silver is not active or reactive enough to replace the copper in this reaction. Let's go now and look at examples that involve the activity of halides. Okay, so we're going to look at those halogens. In this example, we'll take fluorine, diatomic fluorine, F2, and see if it reacts with sodium chloride. Okay. Now in this case, the element that's by itself is fluorine, which is a nonmetal. So we have to compare that to another nonmetal in this reaction, which would be the chloride. So our question is fluorine more active than chlorine? Well, we look over to the right and we see fluorine right here and chlorine right below it. So fluorine is higher up on the activity list than chlorine, so this reaction does work. And we get Na plus and F minus, and Cl, chlorine is diatomic, so it's Cl2. Now this together, if we balance the charges, would give us NaF. Okay, so this reaction is successful. An example where this reaction is not successful, let's take bromine with that newly formed sodium fluoride. We want to know, does this reaction take place? Well, we look for bromine. Bromine is right over here on the chart, and fluorine is up above it. So the fact that in this example, bromine is less reactive means that it doesn't have the chops necessarily to kick out fluorine. So the result is no reaction. Okay, so this is activity series. Activity series of metals is just between the two metals, and activity of halides is just when we have the halides. This chart is available at the back of your course pack on the inside back cover. Let's go now to double replacement and review that. So in this one, we see that two compounds are going to switch partners. As evidenced here by the products, A switches places and takes D, and C goes to be with B. And those are our two products. So the result is that there are two compounds on both sides of the arrow, or both sides of the reaction. Okay. Now, usually one of the new compounds, it says, is a precipitate or water. We saw in the last lecture video that the example where water is a product would be in a neutralization reaction. Okay, and this is an acid-base neutralization reaction. So here, an example of this, let's say we have KOH, which is a strong base, an aqueous, reacts with sulfuric acid, a strong acid, that's also aqueous. And for double replacement, the K is going to go be with the sulfate, and H is going to go with the OH. And of course, we have to keep in mind the charges of each component and how they balance out. And so our result is K2SO4 for potassium sulfate, which is aqueous, plus water, which is a liquid. To balance it, we need two KOHs and two waters. All right, but we see that there are two waters that were formed here. Which that doesn't work. Okay, so the water that's formed here is one of the product possibilities of a double replacement reaction. Let's look at the case now where we have a precipitate. To do this, we need to use something called a solubility chart, which is this thing over here. And this refers to a chart with a list of ions, anions on top in this specific one, and cations over on the left. And so when we mix the cations and the anions together, we can see what happens if a precipitate is formed or if it remains aqueous in water. So you see different designations up here at the top left. If it's a big acid solid, SAQ is slightly soluble and AQ is aqueous. Generally, and this is the key to help us with this, is generally if it's a solid or slightly soluble, then it forms a solid in double replacement reactions, meaning that we have made a precipitate and the reaction works. So let's practice using this table. Let's take calcium ion plus 2 and bromide. First we need to find calcium, which is here, and bromide is up here. We track it down, we find that the result is aqueous, and so that means that a salt or ionic compound of calcium bromide would be soluble in water. Another example, we take magnesium and let's say carbonate. And so for these, we look up just where is magnesium? Well, magnesium is right there, and carbonate is over here. And so as we track it down, we see that we have a big S, which signifies for us that this is insoluble or a precipitate if it's in a reaction. So we put it in water and it should be unable to dissolve. All right, let's look at a couple examples. The first example, we're going to show where we do get a precipitate. And in this example, we're going to take lead 2 nitrate, which is aqueous, plus potassium iodide. We want to know, does this reaction work? All right, so for double replacement, the cations switch partners. So this Pb will go with I, and K will go over with nitrate. So we've got Pb plus 2, it's lead 2, and iodide, which is a negative. So let's utilize this on the chart. We look for lead, which is right here, and iodine, or iodide right there. We track them and we find that it's SAQ. This means that in our double replacement reaction, it makes a solid, a precipitate. So we can crisscross the charges and we get PbI2, that is a solid, it's a precipitate. And then we're going to look over at the K and the NO3. We have K and nitrate. Oops. So we have the potassium here, and the nitrate is here, and it is aqueous. In fact, if you notice, anything that's potassium or sodium for that matter, so sodium, potassium, basically group 1 metals are all aqueous, and you'll notice that nitrate, every nitrate is also aqueous. Just something to keep in the back of your mind. If it has a nitrate, it's aqueous. If it's got K, potassium, or sodium, those are also all aqueous. So all that to say, we get KNO3, but it's aqueous. Okay. The important thing here is that we made PbI2, which is a solid. It was a precipitate, so this reaction is successful. This now will be an example where this doesn't work. Let's say we have sodium iodide, aqueous, which we just said anything with sodium is going to be aqueous anyway. And to this we add magnesium acetate. And we want to know, does the reaction work here? So our partners that are going to switch, sodium is going to go be with acetate, magnesium is going to team up with iodine. So Na and acetate, C2H3O2. So we look up sodium, Na. We said anything sodium is going to be soluble. In fact, acetate here makes it aqueous. Okay, so it's aqueous. Plus, and then we have magnesium, which is a +2, and iodide. Okay, so magnesium here going to iodide, and that's aqueous. So in this example, after crossing the charges there, we end up making 2 aqueous compounds as a product. That means that these ions were all, it was aqueous, they were in water, they mixed around, but they didn't collide enough to make a substantial product here. That when we mix them, there just is no product that's made. So instead of going through and writing out all the products as we did, if we can identify from this point and this point here that both products are aqueous, rather than writing out the products and predicting them, we simply write NR for no reaction. That's it.